Hello everyone, my name is Jayaditya. Today's topic about movements. How movements are help in statistics probability and the probability density function. What are movements? Movements are the specific quantity measures used to describe the shape and characteristics of a random variable in the probability density function. Gives the essential information about the data. It gives the shape, spread and the location. Momentum gives the crucial information about shape, spread and the location of the probability density function. It helps us to understand data and their behavior. Why movements are important? Movements are fundamental tools in statistics for several key reasons. Some in this they condense complex density properties in a few numerical values. They provide standard ways to compare two different data sets of a random variables. Key types of movements. There are two primary key types of movements. Each provides different insights into a distribution. One is movement about the origin and another one is movement about the mean. If you see here, movement about the origin, this movement gives the calculation to the zero. They are generally used to describe the absolute position and spread of the distribution. The first momentum is called mean, and higher order movements gives the less insights of their own. Movements about the mean. It is also called the central movements. These movements gives calculate related to the distributed means. They are crucial for describing the shape of the distribution and also independent of its location. The first central momentum is always zero. The second central momentum is the variance. If you go to the higher order, central momentum describes skewness and the kurtosis. The first momentum, mean. Movements about the origin. First momentum about the origin is denoted by m1. It simply gives the arithmetic mean or expected value e of x of a random variable. X indicates the critical value of the average value of the distribution. Mathematically, nth order is defined as mn equal to e power x power n is equal to integral minus infinity to infinity x power n fx of x dx. For a discrete random variable, e of x power n is equal to summation psi power n into p of x. For example, if you collect the student's testing score, the first momentum gives the average of the class. Case 1, if n equal to 0, then m of 0 is equal to integral minus infinity to infinity x power 0 fx of x dx equal to 1. Here x power 0 gives the 1 and fx integral minus infinity to infinity fx of x dx gives the area under probability density function 1. So the 0th momentum m not equal to 1 gives the area under PDF. Case 2, if n equal to 1, m1 equal to integral minus infinity to infinity x into fx of x dx. It is the expected value e of x. So the first momentum is equal to the mean value or expected value m1 equal to x bar. In case 3, if n equal to 2, m2 equal to integral minus infinity to infinity x square fx of x dx equal to e of x square. The second momentum represents the mean square value of the x. Note, if x is a random signal, gives the average value of the signal and root m1 gives the average value of the signal and root m2 gives the RMS value of the signal. Movements about the mean. It is also called central movements. It is denoted by mu. General formula. The nth central momentum of x is given as mu n is equal to e of x minus x bar whole power n is equal to integral minus infinity to infinity x minus x bar whole power n into fx of x dx. For discrete random variable, it becomes mu n is equal to summation xi minus x bar whole power n into p of xi. If you see n case 1, when n equal to 0, mu naught equal to e of x minus x bar whole power 0 equal to integral minus infinity to infinity x minus x bar whole power 0 fx of x equal to 0. Anything power 0 gives 1. Mu naught equal to fx of x, mu naught equal to integral minus infinity to infinity fx of x dx. It is the area under probability density function, so it is 1. Mu naught is always equal to 1. This means the zeroth moment central momentum is always 1. On, if you see here in the origin, the zeroth moment is m naught is equal to 1, and here central momentum zeroth central momentum is also 1. Case 2, when n equal to 1, mu 1 is equal to e of x minus x bar is equal to integral minus infinity to infinity x minus x bar fx of x dx. On expanding this, we get mu 1 equal to integral minus infinity to infinity fx of x dx minus x bar into integral minus infinity to infinity fx of x dx. For this, integral minus infinity to infinity x into fx of x dx is the mean value x bar, and minus x bar integral minus infinity to infinity x bar is, this is the area under PDF, so this value gives 1. So mu 1 is equal to x minus x bar is equal to 0. The first central momentum is always 0. On the origin, the first central momentum is equal to mean value. Here the first central momentum is equal to 0. The second central momentum, it gives the movement about the mean. It is denoted as mu 2 and it gives the variance sigma square. It measures the spread or dispersion of the data points. For continuous, mu 2 is equal to sigma x square equal to e of x minus x bar whole square is equal to integral minus infinity into infinity x minus x bar whole square fx of x dx. For discrete random variable, sigma x square equal to summation of xi minus x bar whole square into p of xi. The third central momentum gives the skewness measure in asymmetry. The third central momentum is denoted by mu 3. It provides the skewness of the distribution function and the asymmetry. It indicates whether the tail of the distribution function is one side or another side. Positive skewness. It gives the longer side of the right side when mu 3 is greater than 0. The incomes distribution where a few higher earns put the average up. Negative skewness is longer side of left side. Mu 3 is less than 0. It gives the common data. For example, like exam scores where most students do well but a few perform poorly, like 0 skew. The distribution is asymmetry. Mu 3 equal to 0, like a perfect bell curve. In this slide, you see all the central momentum value. If n equal to 0, mu naught equal to 1 is the first 0th central momentum always gives equal to 1 area under. If n equal to 1, the first central momentum mu1 equal to 0, it always gives 0 value to balance out. If n equal to 2, the second central momentum calls the variance mu 2, measures the spread dispersion of the data about the mean. If n equal to 3, it gives the skewness, indicates asymmetry of the distribution. If n equal to 4, gives the kurtosis related. If you see an example, find the variance of x for a uniform probability density function. The uniform probability density function given by fx of x 1 by b minus a, limits tends to a less than or equal to x less than or equal to b, then the variance is sigma x square equal to e of x minus x bar whole square. Variance sigma x square is equal to integral minus infinity to infinity x minus x bar whole square into fx of x dx. Here x bar value, we don't know x bar value, so that x bar equal to integral minus infinity to infinity x into fx of x dx. Here fx equal to 1 by b minus a, limits tends to a to b. So x bar equal to integral a to b x in by b minus a into dx. On integrating this, we get x square by 2 into b minus a of limits a to b. By applying the limits, we get b square minus a square by 2 into b minus a. On expanding this to solve, finally we get x bar is equal to a plus b by 2. On substituting the x bar into this equation, we get sigma x square is equal to integral a to b x minus a plus b by 2 whole square into 1 by b minus a dx. On further expansion, solving, 1 by b minus a is constant, and integral a to b x square plus a plus b whole by 2 whole square minus x into a plus b of dx. On solving, 1 by b minus a x cubed by 3 plus a plus b by 2 whole square into x minus a plus b into x squared by 2 under the limits a to b. By applying the limits, 1 by b minus a into b cube minus a cube by 3 plus b whole square by 2 into b minus a minus of a plus b by 2 into b square minus a square. On further expansion, we get b minus a by b minus a into a square plus b square plus ab by 3 plus a plus b whole square by 4 minus a plus b whole square by 2. A square plus b square plus ab by 3 minus a square plus b square plus 2ab by 4. On expanding this, is 4a square plus 4b square plus 4ab minus 3a square plus 3a square minus 3b square minus 6ab by 12. A square plus b square minus 2ab by 12 we can written as a minus b whole square by 12. Therefore, sigma x square is equal to a minus b whole square by 12. Sigma x square is the variance. The variance value is a minus b whole square by 12. For the conclusion, we get key points take away from next step on the movements. Movements are dispersion. Remember that movements are numerically summarized the capture the location, mean, spread means variance and asymmetry of the skewness and tailedness of kurtosis of the distribution function. They form the basis for many advanced statistics tests and model allowing to deep insight into the data. To solidify your understanding, practice calculation these movements for various discrete and continuous probability density function. It helps simply like in discrete and continuous in the probability density function. Thank you for watching.